guys, just wanted to start in on our second day of applied optimization. This is the last section in our applications of the derivative unit, kind of the crown jewel for that section. So since this is kind of a heavier section at the tail end of this unit, I wanted to give you guys a couple days worth of practice with some problems from it. Now, as you'll recall, I mentioned my red flag for optimization. What do I really mean by optimization? These are all questions where I'm looking for the maximum or the minimum of some sort of a function describing a measurable quantity. Now, I gave you guys some applied optimization problem solving steps the other day, and I have these all laid out for you guys. I'll make a couple notes on these as we recap. The first step in applied optimization problem solving will be to draw and label a picture. So kind of the key idea here is that we really wanted to, if I could get my pen straight, we really wanted to just name my variables and give myself a little bit of a point of reference to what I was calling what throughout the rest of the problem. Next thing that I needed to do was find my function to optimize. Now, typically, this is going to be described by some sort of geometric quantity or relationship for us, just so we can give you guys some problems that you guys can actually set up. A lot of these are based off of volume or area or distance or something like that that's usually okay to piece together with a little bit of brain power. Next thing that we wanted to do, once we had this function to optimize, we needed to rewrite the function in one variable. All of our methods for finding extrema of functions are all single variable methods. So what I need to do is come up with a way that we could apply those single variable methods to our function. Now, as a comment, how do I rewrite this function in one variable? We typically want to use some sort of information from my problem, okay? They're going to give you some sort of constraint or other instruction that you can use to help break this down into a single variable case. On my next step, we've said that we have to note the domain and pick an appropriate extrema test. Now, for this guy, you have two options. Basically, the global test versus the local test. For your global test, remember that's the one that you're working on a closed interval, you've got a continuous function, all your points go back into the original function. Versus my local extrema test, this is where we're looking at breaking our domain up into different intervals using our critical points, and then we're checking where we're increasing or decreasing using the derivative. Okay, now depending on what your domain is, you may be forced to use one over the other. We'll play around a little bit with that today. And then finally, your last of your problem solving steps is going to be to actually answer the question that's asked. So here I will just point out, go back and reread your question. This is really what I'm asking for here in this step. Reread the question and then make sure you actually answer it. And on top of that, once you make sure you actually answer it, give units. Okay, in real life, whenever we answer questions that involve units, we give units in response. So let's go ahead and do that. All right, now we've got our problem solving steps recapped. Let's see if I can set us up with our first example. Example number 1. Comet moves in a parabolic trajectory to the sun. Assuming that we locate the sun at the origin in the xy plane, that units on the x and y axes are in millions of miles, and that the path of the comet follows the parabola y equals x squared minus 2, what is the closest that the comet gets to the sun? Okay, so there's a lot to unpack in this question. First off, let's get a picture going of what my general situation looks like. So problem solving step number 1 was going to be get a picture. I have my xy plane, and what I'm saying that I'm doing here is here's my sun right at this center point, okay, in my xy plane. There's this parabolic trajectory of this comet, x squared minus 2. We should recognize that this is going to be the parabola x squared, but the minus 2 gives it a downward shift. So my comet is following somewhere along this parabola. You could kind of imagine either it comes in from the left and goes out right, or vice versa. It comes in this way, loops around the sun, and slingshots out. This is my current situation. Now, if I read what the problem is looking for, they want to know where the closest is that the comet gets to the sun. So here's my red flag word right here. It said to keep an eye out for these EST words, or, for overt references to maxes and mins, because these are telling you that you're looking to optimize a particular function. Now here my EST says, closest means I want the smallest what? Smallest distance. If you can kind of vision what's happening here, I can track my path of my comet as it comes in, and at any point that I am on this path, I could fix that point and then worry about a distance from the sun to the comet. Or if I was over here, I could fix that point and worry about a distance from my sun to the comet. Okay, so I'll erase those for now, but that quantity, that distance from this point, the sun, to my comet on its potential different points on this path, that distance is what I'm looking to minimize. So let's think about this. I'll go ahead and just pick an arbitrary point on my path just so I can have some labels here. My path is going to be some sort of XY coordinate. Okay, maybe my XY is up here. Maybe my XY is down here, like I referenced before. Who knows? I'll go ahead and let's let my point on my path be some XY coordinate. All right. Now that we have step 1 out of the way, step 2 is going to be to find a quantity to maximize or minimize. Since we want closest, we want to minimize this. Now, as a refresher, I'll go ahead and give you guys my distance formula, right? This is something that hopefully you've seen before, but if not, here we go. My distance between 2 points in the XY plane, I'll go ahead and label, let's say XY, and I don't know, let's give another point AB. This is given by the following function. Okay, I'll call this D for distance at the moment. This will be the square root of the sum of squares, x minus a quantity squared, and y minus b quantity squared. This is kind of based off of the Pythagorean theorem, right? We've got an x distance, that's kind of like a horizontal leg of a right triangle. We've got a y distance, it's like a vertical leg of a right triangle. And if you square both sides, the distance between your 2 points is kind of like the hypotenuse of your right triangle. So this is my distance formula between 2 generic points, xy and ab. Now this is in all sorts of different variables. So let's see if we can whittle that down a little bit. Step 3, how do I turn this into a single variable problem? Because right now it looks kind of crappy. Well, I'm not just dealing with arbitrary xy points and ab points here. My key points are going to be, well, this xy that we've named, okay, the one above in step 1. And where are we concerned about finding the distance to? We're worried about the distance to the sun. And where did we put the sun? We put it at the origin. So that will simplify things quite a bit. My distance from my path to the sun is now going to be given by the following function for D. I get to stick in 0 for A and 0 for B. This is basically just going to give me x squared plus y squared inside of the square root. And I know a couple people are thinking it right now. No, you cannot simplify the square root with the squares, pretty much for the same reason that if you were squaring this whole quantity, you couldn't just square both terms. You would have to FOIL it. Okay, powers won't allow us to simplify in that manner, so we have to leave this as is. Now you'll notice I still don't quite have this down in terms of one variable yet, so I need to do a little bit of extra digging here to get this in an appropriate form. I need to come up with a way to rewrite either y or x, and handily, if I look at the path that my comet is traveling along, I may as well just take that information here and we'll go ahead and sub in y, because the xy coordinate of my comet, this is given by lying on that curve, so I may as well sub in y where appropriate. This means that we'll get, actually let me go ahead and do this over here. We'll get d is, if I sub in that y, x squared plus quantity x squared minus 2 squared. And there's a bit of cleaning up we can do here, just so there's a little bit less clutter when we deal with it later. Like, I can FOIL that out. I'll get x to the 4th minus 4x squared plus 4, or probably in the most simplified form that I can make it right now, d is going to be square root of, I'll combine terms, x to the 4th minus 3x squared, because I had one positive 1 and 4 negative 1s, and then I'll add 4 in the end. This guy is my function to minimize. This reflects my distance between my comet and the sun at the origin at a given x value. Okay? So, next step, what do I do with this thing? Now, as an argument for my next step, I'll scroll down a little bit so I have some more working room here. If I'm trying to minimize this function, one of my next steps was supposed to be to note my domain and then pick an appropriate test. Now, if I wanted to rely on geometric arguments, there's not really any restriction in this picture on what my x values are, right? If we look back long enough in time, we get really increasingly negative values over here, and if we look far enough in time, we get increasingly large x values over here. There really aren't any values in my domain that are ruled out. So here I'll go ahead and note, this is one of those rare cases, x can be anything. So my domain, this is going to be basically from minus infinity to infinity, all the real numbers. No restrictions on this. My comet can be basically anywhere here, at least as far as left-right goes in this diagram. Now, a consequence of this, since we're on an open interval, or rather, since we're not on a closed interval, this means that we have to use my local test. Okay, so let's go ahead and get that going. Apply my local test to this function d right here. Now, this is going to be a little bit of a mess because I've given us a little bit of a complicated function, but let's just scroll down, give ourselves a little bit of room, and see what we can do with this. Okay, first off, critical points. If I'm looking for critical points, I'm going to take d prime and then see what happens if I can figure out where this guy is 0 or doesn't exist. And the chain rule applies here. This is technically that polynomial raised to the 1/2, if you want to interpret it that way instead of the root. So I can view my derivative as 1 over 2 times my square root, x to the 4th minus 3x squared plus 4. This is all times the derivative of the inside. The derivative of that inside function, well, I can multiply it over here to the right of the fraction, or I may as well just leave it up top here and multiply it by the 1. My derivative of my inside is going to be 4x cubed minus 6x up top. Okay? Now some comments here. If I set my top equal to 0, well, let's see what we get. We are going to get, let's see, I can pull out a 2x will be multiplied by x squared minus 3 here, I believe. Yeah, 2x times, 2x squared minus 3. And then if I try to clean this up, this beginning part is going to give me a 0 solution. This part over here, the 2x squared minus 3 being 0, that might force that 2x squared is 3, or x squared is 3/2, or x is equal to plus, let me give myself better space here, x is equal to plus or minus square root of 3/2. Okay? So I've got 3 potential critical points coming from setting my top equal to 0. Okay, 0 and plus or minus root 3/2. Now what happens when I set my bottom equal to 0? If I set my bottom equal to 0, then here's what I'm going to get. I need to probably view this as a quadratic polynomial. I know it's not a quadratic, it's a 4th power. You can see there's the 4th power right here. But this does have some relationships to a quadratic in that, think about replacing your x squared terms with maybe like a y. Then this would look like y squared minus 3y plus 4. That would totally look quadratic. What that means is if we could factor this, maybe we could try breaking this into x squared pieces first and then worry about factoring those. Alright, great. Let's maybe try something like your quadratic formula to see if we could get at least what those x squared terms should look like. Well, if you try this, you'll see what happens. Negative b plus or minus square root b squared will be 9 minus 4 times a times c all over 2a. Well, this part here looks like 9 minus 16 inside of the root. That is negative. So there's basically no solutions that happen when I try to set my bottom equal to 0. Okay, we can't even break this down into squares to break it down more. If we can't even get that far, we can't factor this thing. So no solutions from setting my bottom equal to 0. We don't get anything there, but we do get my 3 critical points from setting my top equal to 0. Now, we're going to go ahead and continue along and apply this in my first derivative test. I needed to mark 0 as a critical point. I needed to mark root 3 over 2 as a critical point, and I needed to mark negative root 3 over 2 as a critical point. Now some comments here. I could plug these into a calculator and figure out decimals and test points and whatnot, but I'll save you guys a little bit of time and make this observation. 3/2 is bigger than 1, so that means the square root of this thing is going to be bigger than 1. 3/2 on the other hand is also less than 4, so that means the square root of this thing is going to be less than the square root of 4. So this is going to be less than 2. That means that this decimal is going to fall somewhere in between 1 and 2. I'm going to go ahead and make 1 and 2 my test points here. And very similar argument, I'll make -1 and -2 my test points here. Now, I'll go ahead and let you guys verify this later on your own if you want, but it doesn't matter which of these I plug into my denominator, they all come out basically positive here. So the key thing that I'm really going to be worried about is what's going on with my top, okay? What happens when I plug in to my derivative? What happens when I plug in -2? What happens when I plug in -1? What happens when I plug in 1? and what happens when I plug in 2. Okay, each of these test points. Now, up top, this will be for this very first guy here, 4 times -8, basically plus 12. I'll just go ahead and do this first one for reference here. If I plug in my -2, this is going to turn into 16 minus 12 plus 4. At any rate, I've got minus 32 up top plus 12. I've got a negative over a positive, right? So this will boil down to a negative. If I wanted to go and verify some of these others, basically I'll have minus 4 plus 6 up top for this guy. This is over 2 times root 1 minus 3 plus 4 down here. Well, this is a positive over a positive. I'll get a positive value. And then if I try the rest of these again, basically I'll get 4 minus 6 here. You can verify me independently if you want. This is over a positive number, so I'm going to get a negative here, and I will get 32 minus 12 again over basically a positive number, so I'm going to get a positive here. This means that if I'm analyzing my signs on this chart, I am negative, then I am positive, then I am negative, then I am positive. So this is actually a little bit concerning at the moment. What this is going to suggest, if I keep in mind what I was looking for in the first place, now it's easy to lose track. If I scroll back up, what I wanted in the first place was the closest point that the comet comes to the sun, so I wanted a minimum of that distance function. Now, investigating this chart, there's actually 2 mins here. There's a minimum this guy, there's a minimum at this guy, because I'm decreasing then increasing, okay? So this sign chart is going to tell me I have a local, specifically a local min, at x equals positive or negative root 3 over 2. Now, I mentioned to you guys before, if you only have one minimum, then it's going to have to be global. But we've got 2. How do I know if maybe this is what my function does? Or maybe this is what my function does? Or perhaps if they actually even out and they both serve as minimum values? Well, here we're going to have to be a little bit sneaky and maybe apply both tests simultaneously. I know that these are mins. Which one's the smaller min? Well, I can take it to my original function to actually see what's going on, right? So what I'm going to go ahead and do is I'm going to go ahead and plug my points into D to check for my min. Now, if I go back and scroll up and take a look at what D was, here's a comment that I'll go ahead and make. If I investigate this guy really quickly, it should be pretty clear that it doesn't actually matter which one I plug in. Both of these guys should give me the same value because all those even powers, those are going to yield my same output at my plus or minus critical points that I got, right? So whether I plugged in this minus root 3 over 2 or positive root 3 over 2, those negative signs are going to cancel and I'll get the same thing. So if I make that observation, it actually turns out we have 2 locations at which we have the same exact minimum here. So I'll go ahead and make note of that. We get the same output. Both are my locations of my global min. Now with that said, I need to make sure that I've actually answered my question here. Have I done that? Well, let's go ahead and scroll back up one last time to double check what they were looking for. What is the closest that the comet gets to the sun? Okay, so what that's going to tell me is this, the answer, the locations of the min, okay, you know, they're probably going to be over here and over here somewhere. This is why they look about the same, because this is symmetrical. It's not good enough to give the locations. I actually have to give the distance in terms of millions of miles. So we'll go ahead and plug this in really quickly. So d was x to the fourth minus 3x squared plus 4, all inside of my root, and it didn't really matter which one I plugged in here to get my result. My closest distance was going to be given by plugging that root 3 over 2 in here and then simplifying. So basically this many million miles, okay, whatever this simplifies to, is the closest that we get. Okay, and since I don't want to bore anybody with the algebraic simplifications here, if you guys are worried about the actual number, I'll let you multiply this out on your own. Okay. Now, let me see if I can do one more of these. I'll try a slightly different example, maybe that I can try with a different test here. So this one maybe might strike a little bit more close to home, you know, at least with stuff that you've interacted with before. Let's suppose I'm looking at cylindrical cans who have a particular surface area. I'll go ahead and ask what dimensions yield the largest possible volume of the can. The reason that I say that this is probably going to strike closer to home, I mean, who hasn't gone to the grocery store and bought something that comes in a can, right? Manufacturing companies make billions of those things every year. It's pretty reasonable that maybe there might be some optimization in question when they're thinking about how to package their products, right? How can I pack the most within a given surface area? Now, if this is a question that I'm worried about, well, here's my picture. All right, I've got my can. It's probably got some radius and some height to it. How do I get my largest possible volume here, right? So what I'm worried about, maximizing my step 2, my function to optimize, this is going to be volume. I want a largest possible volume, so that means I want a maximum volume. Now, what the heck is volume here? Let's go ahead and try for volume of a cylinder. If you don't know that formula, it's going to be pi r squared h. Basically, the area of the base times the height. Okay? Now, step 3 for us was going to be to rewrite this as a function in one variable. Okay, how do I do that? Well, there's this restriction that we have that my surface area, okay, my surface area, this is supposed to be 50 square inches. Now, what goes into the surface area? There's going to be basically the base for my cylinder, the top for my cylinder, and then the sides of my cylinder. Now, as comment about the sides of that cylinder there, what I'm going to imagine happens is if I cut this guy along the side, okay, so I'll actually slice this thing here, and then once I've sliced this thing around the side, I'm going to unroll it. Now you'll notice that this edge here comes from whatever your height is, and this edge here actually comes from whatever your circumference was for your circle. So, to figure out your total surface area, you basically want the area of that rectangle plus the area of your two circles. Okay? The rectangle is going to be the circumference by the height. That is 2 times pi times r times h. And then your two circles are going to be 2 times the area of a circle. Well, that's pi r squared. So this thing is what we're saying is coming out to 50. Now I'll go ahead and make an observation here. And a lot of the problems that we've worked with before, it didn't really matter what we solved for. Here, probably the easier thing to solve for is h, because it only appears once in this expression. So I'll go ahead and solve for that guy. If I do that, 2 pi r is 50 minus 2 pi r squared. Here, oops, I didn't copy over my h. If I'm solving for h, I can now divide by my 2 pi r. So h should end up being 50 minus 2 pi r squared divided by 2 pi r. Now, what I wanted to do was, again, the whole point is trying to optimize my volume by rewriting it as a single variable function using h. So I'm going to actually combine those guys together, right? We will go ahead and let volume be pi times r squared times this h, okay, this guy right here. And I'll notice that there are actually a lot of cancellations that happen. First off, I'll note these in a different color. My r on the bottom and one of my r's up top are going to go away. My pi on the bottom and this pi are going to go away. Another comment that I can go ahead and make is that both of the coefficients in the numerator are divisible by 2, so if I wanted to get rid of this 2, well, that guy can go away, and then this can get replaced by a 25. So, all in all, if I wanted to clean this up, I'm really left with just that one r on the outside that hasn't canceled yet, and then a 25 minus pi r squared. Right, so here's my r times 25 minus pi r squared. If I want to give myself just a little bit more room here, this is going to be 25r minus pi r cubed. So this is my volume function to optimize. Now, once I've found that guy, what I can take a look at is on my next step here, noting my domain and noting my critical points and extrema-tests that I'm applying them to. Now, if I'm worried about what values of r I can actually use here, let's think about our physical situation. If I'm looking at the cylinder and I want the smallest r possible, well, I really can't go past 0, right? 0 is going to be the smallest that I could actually utilize. So I'll go ahead and take a minimum value for r. It's basically 0. If I wanted to find a maximum value for r, okay, my maximum value for r, well, actually I'll go ahead and make a comment here. My minimum value for r is greater than 0. We have to be positive. If I make r 0, there's basically no cylinder, right? And I can't get a surface area of 50 square inches. So we can go pretty much right next to 0. We can compensate by making a super, super, super tall can. But 0 actually isn't quite physically realizable here, so we won't include it in the domain. On the other hand, if I do want to get a surface area for this thing, I can still manufacture, you know, a can that just has 2 discs on the top and on the bottom. Won't actually contain anything, but I could manufacture it, and it still would meet the criteria of having surface area of 50 square inches. My maximum value for R is when all of my surface area comes from those circles, right? So I'm basically saying when my pi times R squared times 2, when that comes out to 50, this is going to suggest that R squared has to be 50 over 2 pi, or 25 over pi, and this is going to say that your maximum value for R is going to come from, well, the solution to this is plus or minus root 25 over pi, or plus or minus 5 over root pi. I'll go ahead and note, you know, only my 5 over root pi counts here because we were looking for a maximum value for R. So, all told, here's my domain. My domain is going to be from 0 to 5 over root pi. Okay, well, this means we can't quite do the global test. We're going to have to shoot for the local test one more time. So let's see if we can actually set up my number line here, right? I'll give you guys my 0. We'll give you guys this 5 over root pi as my number line. And this is my domain that I get to set up my sign chart on. So let's get on finding my critical points, right? For finding my critical points, my v prime, I'm referring to this function up here, that was my v. My v prime is going to be 25 minus 3 times pi times r squared. Well, if I set this thing equal to 0, well, 25 becomes 3 pi r squared becomes 25 over 3 pi, and I note that I should technically get an r equals plus or minus root 25 over 3 pi, or, you know, 5 over root 3 pi, but a comment here, you know, our domain doesn't include the negative value, so we'll not worry about that one. We'll just focus on the positive value. This fraction, 5 over root 3 pi, that's what I'm worried about, right? That's my critical point. Now, this one I actually will give you guys a little bit of a decimal for here. This is going to be somewhere around 1.63. So I'll go ahead and use 1 as my test point here. And this guy, heck, I'll go ahead, since that point is actually included in the interval, I'll go ahead and use 5 over root pi as my test point over here. Why not? What I do with these is I stick these right back in my derivative. So I'll take v prime of 1, and I'll take v prime of whatever 5 over root pi is, who knows. These have to go into this function, 25 minus 3 pi times r squared. So here, this will look like 25 minus 3 pi. Remember, pi is about 3 point something. That means that we're subtracting off about 9 point something. This is going to be a positive value up here. On the other hand, for the second part, I've got 25 minus 3 pi times r squared. This is 25 over pi then. I basically got 25 minus about 75 over here. So this is going to come out negative. If I'm doing my sign test, that means that I am increasing and then I am decreasing. So indeed, I actually do hit a maximum at whatever this 5 over root 3 pi is. Now, we're not quite done yet. I have to go back and double check what they actually wanted here. If I scroll up and look at my question, what dimensions yield the largest possible volume of my can? Okay, so I want to figure out what my dimensions are going to be here. Now, my H, this is given by this guy. If I wanted to, I can go ahead and plug this back in to figure out what my H was. So I'll go ahead and keep that in mind. 50 minus 2 pi r squared. Oops, 50 minus 2 pi r squared over 2 pi r, I think? Yeah, over 2 pi r. So some comments on this. If I want to substitute this location in, this 5 over root 3 pi, well, this guy, 5 over root 3 pi squared, becomes 25 over 3 pi. Down here, my 5 over root 3 pi just stays right on there. If I want to clean this guy up, there's a number of cancellations that I can take, namely like that guy. That means that I can actually subtract this over here. This is 50 minus 50 thirds. So let me actually clean that up. 50 minus 50 thirds all over basically 10 pi over root 3 pi. If I found a common denominator up top and subtracted, I've basically got 150 thirds minus 50 thirds. So I'll have 100 thirds on top and 10 pi over root 3 pi on the bottom. If you are dividing by a fraction, you're really multiplying by a reciprocal. So that means I've really got this root 3 pi over 10 pi down here. I've got some cancellations I can take care of as far as that goes. Other cancellations that I can go ahead and take care of if I desired would be 1, if I split this up and thought of this as root 3 on top times root pi, okay, root 3 times root pi, well, these will cancel and I'll just be left with a root pi in the bottom. Similar deal, I've got a root 3 on top and a 3 on the bottom. If I wanted to cancel those out, I could think of there as being a root 3 on the bottom. After all of those stupid cancellations here, you know, you'll see that I'm basically just left with this 10, this root 3, and this root pi. So, long story short, here is my height, okay, and up here, way up at the top, this guy was supposed to be my radius. Now, keep in mind what this is basically saying. My height is twice what my radius came out to. Right, so my dimensions here, my dimensions were supposed to be 5 over root 3 pi inches, and my height was supposed to be 10 over root 3 pi inches also. Right, these gave me my maximum volume. Now, a couple comments regarding this, since this was what wrapped up our question. This was pretty intense, right? Both of these examples were pretty intense. Now, the main reason I bring them up is I wanted to kind of show you guys how tricky some of these actually can be if we're dealing with slightly more practical examples. And this is kind of why we give you guys the sort of trivial looking, you know, find two numbers whose sum is a minimum and product is, okay, those break down a little bit simpler because, there's less complicated stuff going on than stuff like this guy. On the other hand, though, this is just scratching the surface as far as what you might run into for an optimization problem. We're just giving you guys one constraint, one thing that we might want to find an optimum function for, but just as a demonstration of the kinds of things that you maybe might run into a little bit more in the wild, this problem was very related to, and I'll pull up a link here, this can problem that I posted at this link. So this is a blog post that I found, this guy actually, right here, on why cans end up being shaped the way they are. Now again, billions of these things are manufactured every year, so optimizing volume and surface area for manufacturing purposes is probably going to be a really practical thing to worry about if you're a company that manufactures these things. First off, there's a reason why it's a cylinder instead of a sphere versus a square. There's packing considerations, there's strength of the can considerations. On this page, they actually did a slightly different problem to us, but came out with a very similar response. The most efficient can is going to be the one where the height is twice whatever the radius was. That's basically what we found. The catch, though, is if you actually look at cans in the wild, they went and plotted efficiency of these things, height to radius ratio, how far off are these, and some cans fit pretty closely, some of them are really, really far off. Reason being, optimization problems in the wild get stupid hard because there's lots of considerations to take in. This is kind of the reason why we're going to scale things back on Monday. You guys are still learning this stuff. There's all these kinds of considerations down on the list. Oop, let me not log out here. All these considerations on the list that, there's other things that fall into optimization problems than just maybe one constraint. Examples they give, shape of the can for holding stuff, if, you need to reach your hand in there or not. Marketing reasons, because aesthetically certain shapes look more pleasing. Packing considerations, can you fit stuff in a box easily? What cost is the box going to be to ship? So this actually is a section that has very, very, very useful applications out in the wild. But again, we kind of have to start you guys somewhere simple, right? So we're probably going to be scaling back some of our questions a little bit next time to stuff that's a little bit more test reasonable. Okay, less crazy numbers, less crazy critical points. But I did want to demonstrate, very, very useful application in the wild. But again, we have to start somewhere. So if anybody has any questions, feel free to email me. If not, we'll be working on a couple more examples of this technique on Monday.